Okay, this problem involves forces and motion, and the motion is going to be constant, right? The acceleration is going to be constant. All the forces are constant. It's not changing direction. So this can be done either with Chapter 4 techniques or Chapter 5 techniques. I'll solve it using both. First, a free body diagram. This thing is on the ceiling. So there's my mass. And we have an applied force that makes an angle of 58 degrees with respect to the horizontal here. We also have gravity acting on this thing and a normal force. Remember that the normal force points out of the surface. It's perpendicular to the surface and out of the surface. It does not point up in this problem, it points down. The mass is moving across the ceiling in this direction, so there's the direction of motion. I'll make up positive and to the right positive in this problem. And then there's kinetic friction acting on it, which points to the left. Right? The force of kinetic friction always opposes the motion. So there's my free body diagram for this mass. I've accounted for all the forces. There's no spring force, so there's no tension in this problem, so that's it. Now it's just a matter of solving it. If you have not already solved this problem, then you should take some time to do that now before you watch the rest of the video. I'm going to start with the forces technique, and then I'll do the work energy technique. So let's start with some force equations. For my x forces, I've got the horizontal component of the applied force, right, that's here. This is F applied cosine 58. There's also a vertical component of the applied force, which is F applied sine 58. Okay, what else is in the x direction? Kinetic friction. That's equal to ma. In the y direction, I've got the vertical component of the applied force, which is positive, it points up, minus gravity, points down, so it's negative, minus the normal force, which points down, it's negative, and that's going to sum to 0. Right, so I've got two equations and two unknowns, right? My unknowns are the acceleration and the normal force. So I need to solve one of these equations for the normal force. Let me solve this equation for the normal force, and then I'll plug that in to my x equation. So the normal force is equal to F applied sine 58 minus mg, which is 17.2 newtons. Okay, so I'm going to plug that in. So there's my normal force. Okay, I'm going to take that value of the normal force and I am going to plug it in right up here. So that equation becomes and if I plug in everything I know, the coefficient of kinetic friction is given as 0.22. The mass is given as 3 kilograms. I can then solve for A, so I get 29.15 minus friction, which isn't much, but it's there, and I get A is equal to 8.46 meters per second squared. Okay, now I can solve this problem by using my motion with constant acceleration. So I'm told that we're moving 5.0 meters across the ceiling, starting at rest, and have an acceleration of 8.46 meters per second squared. That means that I'm going to use this equation that doesn't have v in it. So that gives me time of 1.1 seconds if I round off. So there's the problem solved using the force technique. Now I'm going to solve the problem using work energy. So the way the work energy theorem works is we start by determining the amount of work done by all of the forces. The work done by gravity 0, normal force is 0. Both of those are perpendicular to the motion. Let's see, the applied force is going to be the force times the displacement times the cosine of the angle between them. Right? Remember that the applied force points 58 degrees above the horizontal. So if I put the two tails of those vectors together like that, then the angle between them is 58 degrees. Yeah, so that works out to be, the applied force is 55 newtons, delta S is 5 times cosine 58, so that works out to be 145.7 joules. Now, work done by kinetic friction, that's going to be the force of kinetic friction times delta S times cosine 180. Because the force of kinetic friction is in the opposite direction, so that cosine 180 gives you a minus sign, and then we plug in the values that we know already to get minus 18.9 joules. So if we sum the works done by all the forces, is 0 plus 0 plus 145.7 minus 18.9. That's 126.8 joules. That's equal to the change in kinetic energy, which is 1/2 mv squared minus 1/2 mv naught squared. But of course, it starts at rest, so that term is 0. And that gives me v is equal to 9.19 meters per second. But I need time, so I've got to take advantage of the fact that, again, using my equations of motion, let me look at my assumptions again here. We're running out of room. So delta S is 5, V naught is 0, V is 9.19. Okay, so if I use that information to solve, I get delta S. I use the equation that doesn't have A in it. 1/2 V naught plus V times T. That gives me 5 is equal to 1/2 times 9.19 T, which results in T equals 1.1 seconds. So, same answer. Good. All done.